Hello students of statics, this is Dr. Dan Baker, and in this video I'm going to be using this table which comes out of section 5.1, or it's actually table 5.1, also section 5.1, in our engineering statics textbook. And instead of redrawing all these different objects, I'm going to be actually showing them here. I'll also be inserting some chunks of video that have a physical demonstration using some Legos of each one of those, so hopefully you can kind of get your head around not only physically what they might look like, but then also what type of reactions we get from these physical normal supports, okay? So as we go through this table and we talk about each one of these different kinds of supports, realize there's a very fundamental relationship between what the physical support is and the kind of reactions that come from them. And that physical relationship is based upon the following two statements, and that is that support forces will always resist translation and support couples will always resist rotation. Okay, and it turns out for two-dimensional supports and reactions, there's only a few support couples, and those can be down toward the bottom of this table, but there's quite a few different kinds of support forces. Okay, so let's go through these, and I've clustered these into what type of reactions, basically how we can quantify what the support is and the kind of reaction that comes from it. And so fundamentally in this table, you'll find that the physical, kind of the problem sketch type drawing will be on the left, and then its implication on your free body diagram is going to be over on the right. Okay, the kind of forces and or couples that come from the physical connection after we've isolated that connection, or basically the body away from the connection. Okay, so there's 5 different types of supports which give us a single normal force. That normal force is always perpendicular to the surface. And those include a smooth surface. Keep in mind, smooth always means a friction-free surface. We have a roller, and we're assuming this is a frictionless roller, so the roller can roll freely, but then the wheel basically can move up and down that surface without any friction. Now realize that all of these are drawn, and I know sometimes my hand sketches, I put some hash marks here. So this is like your surface that it's rolling along. And it turns out that rockers and rollers, fittingly, both have the same kind of support forces, that single normal force perpendicular to the surface. Additionally, a pinned collar on a smooth rod acts just the same way as a smooth pin or roller inside of a slot. Okay, any of these 5 provide one single normal force. Now, in general, we can assume that this normal force is going to be either pushing on the object or could be pulling on the object. Of course, if you look at these different types, you probably see that certainly the pin collar on a smooth rod and this pin or roller in a slot, these are really the ones that could support pulling, while these other ones here, it's just going to be the surface pushing up on those members. But keep in mind, as you draw your unknowns on your free body diagram, in this case, draw your reactions, it doesn't technically matter which normal force you draw, either pushing or pulling, because your math will double check it. Okay, whatever value you get from your mathematical computations, you check the sign. Okay, if the sign is positive, it means you assumed the correct direction for that force. If the sign is negative, it simply tells you your hypothesis of the direction of a reaction was incorrect. Not a big deal, it's just saying you need to flip it around. That's actually going the other way. And so in that case, if you assumed a pushing normal force, say from this pinned collar on a smooth rod, you solve it out and you get n is equal to minus 10. You then know that it actually, instead of pushing on that member, is actually pulling on it. Okay, so it just tells you that from the negative sign. So now let's take a look at some of those physically. So let's assume that this is our surface, okay, this white piece of Legos. And so if we have a smooth, okay, so a no friction contact between a member and that surface, it turns out the normal force is always going to be perpendicular to this surface. Okay, so it doesn't matter, and I'll try to put my finger here. So if our surface is vertical, the force is horizontal, no matter the angle at which this member contacts it. If I rotate this around, I'm going to end up still with this normal force perpendicular to this surface. Okay, normal perpendicular to a surface always. If I have a different kind of body interacting, let's say that I have this roller here, I still end up with that perpendicular force, always perpendicular to the surface. So it doesn't matter at what angle this wheel is coming in, I end up with a force that's perpendicular to the white piece right here. It's also true for a rocker. So here is a rocker. Now we're assuming that the rocker can essentially go back and forth, but still is providing a normal force perpendicular to the surface. Another one that we have is a collar on a smooth rod. So here is a little demonstration of that one. Ignore the pieces out to the right and left, but essentially here we have a smooth rod. It can slide back and forth. It doesn't matter what angle that the member comes in, there's always going to be a force coming perpendicular to the rod. And so if the rod is vertical, that force is horizontal. And so all of these, once again, are normal forces. And then additionally, the smooth pin or roller in slot is going to act exactly the same way. Moving on now with two force supports. We talked a bit about two force supports back in chapter 3, that essentially a two force body is a body with only two forces by definition, and those forces are equal, opposite, and share the same line of action. Okay, so fundamentally the force at one end is exactly equal to the force on the other end. And so there's three types of two force supports. We could have a cable. Cable's of course flexible. We could have a weightless link and a spring. Okay, so those are fundamentally the three different types. I actually just found a error here. I like using delta for my displacement, and so instead of having delta times x, this should be delta times k, where k is the spring constant. Okay, k is your spring constant in force per length, and so if you multiply that force per length times a delta, delta is the displacement from neutral, you end up getting basically force per length times length is equal to a force, so it gives you your force F. And this shows, of course, again, we have one single reaction force, very similar to our normal supports. It's just that these come from two force members instead of contacting some kind of a surface. So the same implication for your free body diagram, just coming from a different place, different type of support. So let's take a look at some of those physically. Okay, the first two force member we'll look at, this is a little wire tie that I have, but it'll act as a cable. Sorry, I'm looking at here kind of white on white. But essentially, if I push on this, it won't hold any compression. But if I pull on it, it will hold tension. Okay, so it turns out that cables are available only for tension forces, but it doesn't matter how I pull on this. If I leave my left hand here and I move my right hand up, you can see that that member moves with it. Okay, we're assuming no resistance to bending, but it's always going to be basically in line with the connection points on the end. It's going to be the same thing for a weightless link. Okay, so this piece in the middle here, the darker gray piece, I'm assuming is my weightless link. And so however I pull on these two ends, you can see that that weightless link is going to fall in line with that tension. Okay, so it's always just going to be basically, I'm showing here in tension. Now a weightless link can also hold compression. If I get these forces in line, I'm actually pushing on either side toward the middle here, I can actually create a compression force as long as I keep that in line. But a weightless link is a two force member, and there's a single unknown, which is the magnitude of the force inside this. Its direction is always directly in line with that member. So if this member is vertical, the force is vertical. If it's horizontal at an angle, it is at an angle. The last two force member that we have possibly is a spring, and let's hold on to this one here. So essentially a spring acts kind of like a cable, that it can be in tension. So I'm pulling here this cable, this spring in tension, but the additional thing that a spring does is the spring is actually pulling back on my fingers using Hooke's law. That force is equal to F is equal to the displacement of the spring. Okay, displacement meaning that this is the neutral spring, unstretched, uncompressed, and if I pull on this, basically the change between neutral to the pulled length is going to be my delta, and then that's going to be times my spring coefficient, which is K. Okay, so F is equal to delta times K. And you do the same thing for compression. Now, this isn't a great compressive spring because it's a little, it wants to buckle, but I can push on it here if I kind of control my forces, and I can also compress it. And so in this case, it's actually pushing back on my fingers. Okay, so springs can both pull and also push, but they're acting as two force supports, that the unknown is the magnitude of that force, and it's directly in line with the spring itself. One of the most common types of supports that we'll encounter in statics is this one called a pin support. Okay, so a pin support is based upon a smooth pin. So it's a friction-free pin or hinge. So it can freely rotate. Now, there are actually two different reactions, noting this is the first type of support that has two reactions that come from a pin support. We can quantify those technically in three different ways, although the favorite tends to be whatever one that you can create two components that line up with your axis system. Okay, so we're assuming here that we had maybe a horizontal X and a vertical Y. We just put two different unknown components, one along each of the axes, and roll with those and solve them out. Another way we can solve for those technically, the unknowns, is with an overall force magnitude that's represented by this F sub r, and then an unknown angle theta. To be honest, that isn't the most efficient way to solve a lot of these problems. For one, you get in some nonlinearities of always having the sine or cosine of an unknown angle inside as you're solving. And then additionally, you end up with two unknowns in each of your sum force x equals 0, sum force y equals 0 equations. And so it just really makes it a little bit more cumbersome, hence why we like to isolate the unknown components in the direction of those axes. And of course, if you rotate your axes, I'd rotate the components. So that's what this middle one's showing, is just to pick other components if you've picked a different axis. So we're assuming here that this black pin is frictionless, that this can rotate friction-free any direction that it wants to go. But if we try to pull on this, and if we want to assume X and Y components to the forces, I could pull this direction. I could also pull or push this direction, and it's not going to move. Okay, so it has a resistance to translation in two different directions, two different degrees of freedom. And so we have two unknowns. Now you could model those as horizontal and vertical. If you wanted to, you could model them as any orthogonal pair of forces that you desired. Maybe you wanted to pick at a 45-degree angle, so you picked along this direction and along this direction over here. That would work equally as well. But remember that there's two unknowns, and those two unknowns can either be represented as unknown force components, which quite honestly is the easiest, or also as an unknown magnitude of a force in the unknown direction of that resultant force. The next type of support we have on the table is what's called a fixed collar on a smooth rod. This actually comes with two different reactions. One of those reactions being perpendicular to the rod itself. Okay, so it's essentially a normal force coming off of that rod, very similar to what we had above. But now this time the collar being fixed means that there's not a pin connecting essentially the member here to the collar here. Okay, those are like welded together. Because they're welded together, when we go to rotate this member, we end up with a resistance to rotation, which is essentially a resistant couple moment that's preventing that member from rotating. So this is one of the trickier ones. The first one we've had with this moment resistance. This is a smooth rod, but instead of earlier where we had that pin coming through the middle here and this was allowed to freely rotate, we can see if we try to rotate this rod, there's actually a resistance to rotation. Okay, so this is the first one of our supports that has a resistant couple at this interaction between the smooth rod and this collar. Okay, and so we call this a fixed collar on a smooth rod. It comes out with two different reactions. One of those reactions is always going to be perpendicular to the rod. So if the rod is horizontal, the force is vertical. If I put the rod here at an angle, that force is always going to be perpendicular to this rod. And then an unknown support couple that's this resistance to rotation, right? I'm bending this member here because of my resistance to rotation coming from this collar. Okay, so two unknowns, a normal force, and a couple which resists the rotation. Next up, we have a member contacting a rough surface. A rough surface is, of course, defined as one which has friction. And so if a surface has friction, we pick up an additional force, which is parallel to that surface. And so still the normal force that is perpendicular, but additionally a force which is parallel resisting motion. I'm not going to belabor that one here because it does show up later in this class. We're going to assume everything's friction-free until the friction chapter. Okay, so once we get into friction, we'll deal with those in more detail. So earlier when we looked at a surface and a smooth object, now we can assume that there's friction between these two, so we can make this a rough connection. And so in that context, essentially, we still have the normal force. Okay, we still have the normal force that's going to be perpendicular to the surface. We're going to pick up a friction force, which is essentially opposing motion. And I won't talk about this one too much because it is the focus of a later chapter in our book. Basically, there's a whole chapter on friction, and so we'll leave that one for now. And then the last one we have here, it's kind of it's the granddaddy of them all. It actually has three different reactions. Keep in mind that on a two-dimensional problem, you can only have three unknowns. Okay, so this will take care of all three of our unknowns. Two unknown force supports, additionally a moment reaction, and this is called a fixed support. Okay, so anything that is welded or bolted or anchored or sunk into the ground is going to come up as one of these fixed supports, and so it will resist forces in two orthogonal directions, whatever two orthogonal directions you pick, as well as resistant couple. Now we may find even for the resistant couple that we've assumed here a negative from the right-hand rule resistant moment. It may turn out that we need a positive from the right-hand rule, but once again, we'll algebraically solve for it and we'll get either a positive or negative value for that couple we're calling M. If it's positive, we know we assumed correctly. If it's negative, we know that we assumed incorrectly. So we say, therefore, M should be going in a positive right-hand rule direction. And so the final reaction we have is fixed. Okay, so if you weld something to something else, if you bury something in the ground, you essentially pick up three different reactions. Okay, so this one is fixed to the white surface, and so I can't rotate it for one. Okay, so it has a resistance to rotation, basically a couple coming from that connection. I can't pull on this, I also can't push on this, and so it has both resistance to a force this direction as well as a force this direction or this direction. Okay, so two forces, and we're assuming here that they're still orthogonal. I could assume one's horizontal and one's vertical, probably computationally the easiest given the system. And then additionally a couple around the middle there. So that is a fixed support providing three reactions. You don't necessarily need to memorize these per se, but you need to understand them. You need to understand where these forces and couples are coming from. And when you have these types of supports and you need to create a free body diagram, you do need to represent the forces and couples coming from each of these types of supports accurately. Okay, and once again, two-dimensional problem, which all of these are basically two-dimensional supports, can only have up to three unknowns. Okay, if you have any more than three unknowns, you know you probably quantified something incorrectly. One last thing I wanted to cover before closing out the video, it has to do with angles. Okay, and it has to do a lot with these normal forces. And so let's say that in this system, we have an angle here of 40 degrees. Now we love 45s, right? Because you never can be wrong measuring a 45 from horizontal or vertical. But saying that we have a surface here of 40 degrees and we have a block sitting on this surface, as we come over here to draw our free body diagram, we need to quantify not only the weight force, but also the normal force. So the weight force here, right, is vertical. And so let's assume on this problem we're using a horizontal X and a vertical Y, kind of our quasi-standard axis system. And then we come in with our normal force. All right, so my normal force here is going to be up this direction, right? Perpendicular to that surface will be my normal force. And we'll assume in this case, maybe we'll add a force onto here, call this force P, make it horizontal, or excuse me, make it parallel to the surface, so call this P. I needed that force in order to make this plausibly in equilibrium. Okay, given the normal force and the weight force alone, I would have had to add in friction or something to get me into equilibrium. But my question is, what is this angle here? Okay, and I'll need that angle because I'll need to divide that normal force into basically take a sine and a cosine to come up with the components along the x and the y. And so I'll show you a trick that I like to use in finding these angles. And the trick is related to, let me bring in this 40 degrees, it actually comes in right here. Okay, that's the angle between horizontal up to any line that's parallel to the surface. So if I take a look at this system, there's a third angle which is here. I'm going to call this alpha. Okay, and hopefully you'll be able to see that basically from horizontal to vertical, that I can write an equation that tells me that 40 degrees plus alpha is equal to 90 degrees, therefore alpha must equal 50 degrees. Okay, that should be straightforward. Now notice also I have another perpendicular pairing. I have a perpendicular pair here from P over to N, right? N being perpendicular to the surface and P being parallel to that surface. And here again, I'm going to call this one here theta. I have, because they're perpendicular, I can sum those angles equal to 90 degrees. And so I could write here that alpha plus theta is equal to 90 degrees. Now we just solved that alpha was equal to 50, therefore theta must be also 40. Now you can go through this proof every time if you want to, but let me give you a rule you can use instead. And so that rule is based upon measuring angles from either horizontal or vertical. Notice that this 40 degrees is measured here from horizontal, while the theta here is measured from vertical. Okay, so if we have a surface that is, in this case, 40 degrees from horizontal, so that basically defines our surface right here. Anything that is perpendicular to that surface, it doesn't matter where it lies upon that surface, anything perpendicular is going to be the same angle from vertical, okay? Because we're talking about it's perpendicular to that surface. So once again, if we have a surface that's measured from horizontal, anything perpendicular to it is going to be the same angle as measured from vertical. We could flip that around and we'd find that if I knew this angle here was 50, and that also tells me that the angle over to N is also 50, okay? Because this is measured from vertical, therefore anything perpendicular to it is the same angle as measured from horizontal. Okay, so that rule works every time as opposed to going through kind of the angle proof to find that angle for theta. Super important to find your correct angles, of course, because if you don't, you'll get the wrong components, the wrong answers, and who knows, the building you're building may fall down or people may get hurt, right, because of your sine, cosine, angle error. So please lock that in. Thanks for your attention today, and I hope you're having a good one.